In this session, we will have a closer look on what information is contained in the powder diffraction pattern. We will look at the properties of the diffraction peak or Bragg reflections that make up the diffractogram. In brief, we will introduce what material properties determine the position, intensity and width of the peaks in the powder pattern. We will need this as background knowledge to help us take the right decisions in data analysis and interpretation later. Now let's have a look at the X-ray powder diffraction pattern of a substance very well known in cements. This is a powder diffraction pattern of halite, for instance. In this powder diffraction pattern we can see the appearance of a lot of peaks, and these peaks appear at a certain position. Another feature of these peaks is, okay, they don't only have a position, they also have a height, an intensity. So that's also important to know as a characteristic. In what can a peak differ as well? That is actually on the width of the peak. So these are the three main properties of one peak, but also of sets of peaks that actually contain the information that enables you to extract, for instance, crystallographic information, but also phase compositional information in the end. Now, let's have a closer look at what determines peak positions. Peak positions are determined by the size and the symmetry of the lattice or the unit cell. The unit cell is the basic building unit of your crystal. It has three dimensions, typically called A, B, and C, if they are different in size. And between these three dimensions, we have angles, alpha, beta, and gamma. Depending on the symmetry, whether your lattice is, for instance, cubic, or whether it's triclinic, one or more of these parameters can be identical. The other important part to know is, okay, one can have, and this is usually introduced in a crystallography course, is what relates the distance between two planes in your crystal and the appearance of a certain reflection, HKL. The HKL plane with a certain interplanar distance d will diffract, given a certain wavelength lambda, at a certain diffraction angle as is established in Bragg's law. That says the wavelength equals 2 times the interplanar distance times the sinus of the diffraction angle, as seen in the previous session. Then, knowing for a certain plane, HKL plane, what is the interplanar distance, one can actually derive what is the unit cell parameter of, for instance, a cubic lattice, using the formula shown here. One can also derive the lattice parameters of much more complicated symmetries, for instance, the triclinic symmetry, in which we have A, B, C, alpha, beta, and gamma, which are all different values. And then one would need to use this kind of formula. Of course, this gets to be a system of equations where for a whole set of HKL planes, and there are distances and diffraction angles connected, and one can actually computationally easily solve these kind of equations once one knows whether the crystal under investigation is of cubic, triclinic, or other symmetry. That about peak positions. Now let's have a look at peak intensities. Peak intensities are determined by the positions of the atom in the unit cell. So this is really where your crystal structure information is used. For a crystalline phase in a multiphase powder sample, for instance, one can actually have this kind of intensity equation for each HKL reflection of that phase. This intensity equation consists of different factors, most of which are not related to the sample crystal structure, but rather to setup of your instrument or the composition of your sample or, for instance, whether there is some preferred orientation of particles in your sample or not. So there is a general scale factor, dimensionless. There is a Lorentz polarization factor, which mostly depends on how the diffraction takes place in your instrument. There is the absorption factor, which takes into account how much of the incoming radiation is absorbed by the sample. And there is a preferred orientation factor that takes into account whether some HKL reflections are over or underrepresented because of the fact that, for instance, some crystallites that have a non-uniform dimension, for instance, platelets or needles, they can actually be solicited more than other kind of reflections. Finally, and most importantly, there is the structure factor. Looking a bit closer into the structure factor, we see where actually all the crystal structural information is situated. So as seen in the previous formula, the intensity of a certain reflection is proportional to the square of the structure factor. The structure factor itself for a certain HKL reflection is actually the sum over all atoms n in a unit cell, and it takes into account for each atomic site, for each atom in the unit cell, the atomic form factor, the occupation of the site by that atom. For instance, it can vary between 0 and 1. Let's say if you have a solid solution series where you have 50% of the time iron and 50% of the time aluminum at that site, then the occupation site number can actually distinguish between, for instance, the scattering between of aluminum and that of iron. Important is the interference term. This term takes into account the atomic coordinates. So where are these atoms located in your unit cell? And finally, there is the Debye-Waller factor, or the atomic displacement factor, that takes into account thermal displacements of your atoms that can actually kind of reduce the intensities of your structure factor. Looking at the first of the parameters that is in the intensity equation, we have the X-ray form factors that actually reflect the nature of the atom itself. X-rays, in fact, interact with the atomic electron cloud. The higher the number of electrons in this cloud, or the higher the atomic number Z, the higher the X-ray form factor will be. This is what is reflected in the slide on the right-hand side, where you can see the periodic table. And in the periodic table, the size of the spheres actually reflects the value of the atomic form factor. So this also means that phases, minerals that contain atoms with a higher atomic number, will reflect X-rays more efficiently. Or light phases will typically have lower X-ray intensities than phases that are typically heavier. The X-ray form factor does not only depend on the nature of the atom, but also on the diffraction angle. This can be clearly seen on the right-hand side of this slide, where we have a comparison between the form factors of iron, oxygen, carbon, and hydrogen as a function of the diffraction angle, here normalized by the wavelength to give a more general treatment of the matter. One can directly see that these form factors really decrease sharply with diffraction angles. This in fact also explains why when we look at diffraction patterns for X-rays, intensities tend to be higher at the low angle site than the high angle site. This is simply because the atoms will reflect the X-rays more efficiently at the lower diffraction angles. The other part of the intensity equation is basically governed by the interference term. This interference term is actually reflecting the position of the atoms in the unit cell. One can see the positions of the atoms reflected in this first formula, where we see the fractional coordinates x, y, and z appearing. These are the fractional coordinates of the atom in the unit cell. This interference term thus reflects the underlying atomic structure in the unit cell, also called the motif. In fact, the interference term is a vector dot product between the position of the atom n, Rn, as one can see here, and the scattering vector q, HKL, in which HKL is the reflection plane. It is important to realize that this interference term is not a smooth function of 2 theta, and that thus reflections with similar d-spacings may really have larger or similar interference terms. This really depends on the positions of the atoms in the unit cell and the interference with the scattering vector. Most of the information, in fact, that is used to calculate the diffraction pattern of a certain mineral or phase is written down in databases and saved, for instance, under a format like crystallographic information files. One can see an example of this at the bottom side of this slide. These files, they contain lattice parameters such as cell lengths A, B, C, or cell angles alpha, beta, and gamma. They contain symmetry groups, space groups, and they contain also for each atomic site the type of atom which is positioned at that site, for instance calcium, the fractional coordinates x, y, z, and the atomic site occupancy. For the calcium site, there is always a calcium atom sitting at that position. For instance, for other sites, for instance the iron aluminum 1 position, they have the same atomic coordinates. However, 85% of the time this site is occupied by iron, and only 50% of the time it's occupied by aluminum. All this information is needed to calculate on this side the position of the reflections, and usually more on that side the intensity of the reflections. When we want to do a proper fitting of a diffraction pattern, it is very important that we have close, reliable starting models. If, for instance, we have a bad starting model, then the calculation routine, the fitting routine, will have a very hard time in finding the correct, refined, fitted parameters in your X-ray diffraction experiment. The last parameter in the intensity equation are the Debye-Waller factors, also called the atomic displacement factors. This factor in fact reflects the thermal vibrations of the atoms in their positions. They are not frozen, they vibrate around the position, which makes it actually the size of the atoms, time and space averaged, is larger than they actually are. This actually leads to destructive interference when your X-rays are being diffracted, and thus leads to a reduction of the peak intensities. Expressions for this effect can be found here, one of which uses the Debye-Waller factor as such, but other expressions exist as well. For instance, one which is more directly related to the mean square atomic displacement, and B, which is often preferred since it has values around 1 and is thus easier to judge. Typically, when looking at atoms and their thermal vibrations, the general rule is that the lighter the atom is, the larger the atomic displacement will be. Heavy atoms like iron will barely move, smaller atoms like hydrogen will move a lot and spread out their electron density or their electron cloud a lot. This again adds up with the fact, for instance, that for hydrogen we have a very low atomic form factor, together with a large thermal displacement, a thermal vibration. This makes it very hard for X-ray diffraction, the experiments, to actually see hydrogen atoms. Their impact on the diffraction pattern will be very low. The last property that we need to look at is the peak width. The peak width actually tells you more about the microstructure of your sample. Not the crystal structure, the microstructure. Typically, the size of the crystallites that are diffracting, or the lattice strain in these crystallites, can be extracted from an analysis of peak width. Peak width and peak shape really depends on the source of your X-rays, the instrument, the optics of your instrument you're using, and also your sample itself. The classical way of treating peak shapes in calculating and fitting powder diffraction files are by using analytical functions. Typically, Gaussians and Lorentzians are mixed as pseudo-void functions and are used to model the peak shape. Since this did not really represent well some asymmetric properties of X-ray diffraction peak shapes, there are extended versions like the TCHZ or the Pearson 7 that can take into account some measure of asymmetry of the peak. On the right-hand side, we can see, for instance, what is the difference between a typical Gaussian and a typical Lorentzian. A Gaussian actually has very short tails, while a Lorentzian has typically quite long tails to both sides from the maximum. Mixing those can give you a good representation of your peak shape by X-ray diffraction. Actually, peak shapes also really depend on the diffraction angle. Typically, they get wider the higher the diffraction angle is. So, for both Gaussian and Lorentzian peak shape functions, one needs to include a dependence on the diffraction angle. The classical approach to this was made or developed by Cagliotti et al. In 1958, and he used, for instance, for the Gaussian dependence, 3 parameters that can be fitted: U, V, and W. For the Lorentzian, he used 2 factors, X and Y, and fitting those to the experimental data enabled to obtain a good fit between the full width of half maximum at lower angles and that at higher angles as well. Using analytical functions is one way of coping with the problem of fitting and modeling experimental diffraction data. Another way is the fundamental parameters approach. Here, one actually starts from the assumption that yes, we can separate the instrumental, the source, and the sample contributions from each other. To do this, one needs to know what is the source profile and what is the instrument profile. The instrument profile can be calculated from optical parameters, and they are actually established by typical physical equations. The source profile is also usually known for commercial sources, so one can easily fix those and then just retain the contribution by the sample broadening. So, if we can separate contributions from the source, the instrument, and that of the sample in the fundamental parameters approach, one can actually analyze the sample texture. One can obtain information on what is the crystallite size and what is the strain on the lattice for certain materials. This can be very important, for instance, in deformation studies of metals. Sizes can be assessed through the Scherer formula. This formula uses the dependence of the full width of half maximum, the width of the peak as a function of the diffraction angle, and enables you to extract a volume-weighted mean crystallite size. Another formula can be used to extract information on strain. In this respect, the full width of half maximum has a tangential dependence on the diffraction angle. Having a look at how both vary over a wider range in diffraction angles can enable one to separate strain and size contributions to the broadening of your peaks. However, this is only possible for pure or very simple metals, for instance, or powders. When we look at complex mixtures of powders, such as a Portland cement, typically the separation between size and strain becomes impossible for a certain phase, and one usually uses an apparent crystallite size to model the broadening as a function of 2 theta. Peak intensities and peak width. These are the main properties that can be used or looked at in powder diffraction patterns to retrieve information on materials. Peak positions relate to the unit cell dimensions and symmetry. Peak intensities relate back to what type of atoms are contained in your unit cell and what their positions really are. And peak width goes back to what is the microstructure, the microtexture of your sample. How large are actually these crystallites in your sample? Or what is their deformation? The relationship between these analytical properties of your diffraction pattern and the material properties have been used in a very wide array of applications. In the next session, we will actually look at how we can best measure an X-ray diffraction pattern and then specifically apply to cements. We will look at the diffraction geometry, the instrument, and then we will look at what are the best settings of your instrument to measure a Portland cement sample, for instance. Also, we will look at what is the best sample preparation procedure for your problem.